continue our examination of analysis of variance, or ANOVA, by providing you an example. We're going to look at a research example, show you how to calculate all the statistics that go into the ANOVA table, where all those numbers come from, so we can calculate the F statistic. We're going to take all of that information and put it into the context of hypothesis testing and then make a statistical decision. A study was done to attempt to understand the influence of different auditory and visual stimuli on how people interpret spoken words. Specifically, we looked at what is the effect of the lack of synchrony between auditory and visual cues when people are trying to remember a set of words. 30 students were randomly selected and put into one of three groups. Each group was shown a movie of someone reciting a list of 50 words. At the end of the movie, the students were asked to recall or remember as many of those words as possible. The difference in the three groups was how the movie was constructed. Group number one is labeled the fast group, and there the sound came before the lip movements. Group number two is a normal group, and there it would be just like speaking or listening and talking to a person normally, where the lips moved and the sound came at the same time. Group three was the slow group, where the lips moved first and then the sound came. These groups, groups 1 and 3, are kind of like watching a movie that's been dubbed into another language, where the lips and the sound don't line up or synchronize exactly correctly. Here's what the data look like. 3 groups, fast, normal, and slow. 10 students in each group. Student number 1 in the fast group remembered 23 of the 50 words. Student number 2 in the fast group remembered 22 of those words, all the way down to student number 10 in the fast group, who remembered 17 words. In this case, the fast group will be J equals 1. If we look at J equals 2, the normal group, you can see the first student remembered 27 words, the second 28, and so forth. And then the slow group is J equals 3. First student remembered 23 of the 50 words, second student remembered 24 of the 50 words. Let's go ahead and look at our hypothesis test first, and then we'll show you how to calculate all the numbers. First step of hypothesis testing is to assume the null hypothesis of no difference. In this case, we're assuming that the average number of words recalled by the fast, normal, and slow group are identical. That is, mu sub 1 equals mu sub 2 equals mu sub 3. Our alternative hypothesis is that at least 2 of those means are statistically significantly different from each other, and we give that as h sub 1 is mu sub 1 not equal to mu sub 2 not equal to mu sub 3. Step number 2, we have to have an idea about the range of possible outcomes of our test statistic. In this case, because we're doing an analysis of variance, a continuous dependent variable, a discrete independent variable with 3 or more categories, we know that we're going to calculate an F statistic, and therefore the appropriate sampling distribution is the F distribution. We can find the table of F distribution on page 468 of your textbook. Step number 3. How much evidence do we need to reject the null hypothesis? That is, how large does our calculated F statistic have to be for us to conclude that the group effect is statistically significant? We use alpha to make this decision, and in this example, I'm going to set alpha equal to 0.05. To look up the F critical, I have to understand that I have 2 and 27 degrees of freedom. That is, there are 3 groups minus 1, so there's 2 degrees of freedom associated with the between group sum of squares. And there are 27 degrees of freedom, or n minus j, the number of students in the experiment, minus the number of groups associated with the within group sum of squares. When I go to the F table in the back of the book, I find an F critical value of 3.35. When I calculate the F statistic for this particular problem, if I get a value less than 3.35, I will fail to reject the null hypothesis. If I get a value that exceeds 3.35, I will reject the null hypothesis with alpha set to 0.05, meaning if I've made a type 1 error, rejecting the null when I shouldn't have, the probability of making that particular mistake or error is 0.05. Here's the F table from the back of the book. Notice at the top of the table we see alpha equals 0.05. You'll find a different table for different alpha values. Notice that the columns and rows are labeled with the degrees of freedom. In this example, I have 2 and 27 degrees of freedom. The between group degrees of freedom are across the top of the table, labeled by the columns, and the within group degrees of freedom are in the rows. I find the intersection of 2 and 27 degrees of freedom, and I find my F critical of 3.35. Again, this is the number that we will compare our calculated F to that we calculate in step 4 of the hypothesis testing. Step 4, go to the real world, collect our data, calculate our F statistic, and in this case, I get an F statistic of 5.895. Step 5, make a decision about your observation, comparing what we observe to what we should observe if chance is operating. Our F calculated here, 5.895, is greater than our F critical, 5.35 or 3.35. So we're going to reject the null hypothesis and conclude that at least two of these sample means are statistically significantly different from each other. Or thinking about it another way, they really come from different populations. Well, let's look at how to calculate this. This table is set up as a spreadsheet, so it's calculating all the numbers in real time for me. You'll notice that I've got a column labeled Group 1, which is the slow group, and there are 10 students in that group. The scores go from 23, 22, 18, all the way to 17. You can see that I have a column labeled DEV squared. And what this column is each individual score, for example, 23 for the first student in the slow group, minus the overall or grand mean, 23.467 squared. Why do we square these things? Well, you remember that if we take the sum of deviations around a mean, they always sum to 0. That's part of the definition of what an average is. It's exactly in the center of a distribution as measured by the weight of the cases around that value. So we typically square these deviations to get rid of the negative values. I repeat this for group 2 and group 3. If I take all of those deviations squared and I add them all up, I get my total sum of squares, or my SS total. In this particular example for calculating SS total, I'm actually ignoring what group a person is in, because I'm looking at the difference or the variability of each recall score around the overall or grand mean without regard to group membership. Here I have a very similar table where I'm calculating sum of squares within. I've color-coded it a bit to make these groups seem a bit more distinct. So group 1 is kind of a dark blue, group 2 is a bit red, and group 3 is a little bit lighter blue. Here, when I calculate SS within, I'm calculating variability as well, or a variance as well, but I'm paying attention to group membership. For example, I'm going to calculate, in essence, the total sum of squares for group 1, and then the total sum of squares for group 2, and then the total sum of squares for group 3, and add them all together. So here I'm looking at variability within group of each test score around the average of that group. So to do this, I need the arithmetic average for each of these groups. For example, the average word recall for group 1 was 21.8. The average word recall for group 2 is 27.4. And the average word recall for the group 3, the fast group, is 21.2. I calculate all the deviations, square them, sum them up, and that gives me my within group sum of squares. The last thing to calculate is the between group sum of squares. I'm going to show you how to calculate the between group sum of squares, but truthfully we could have calculated this based on the previous two sums of squares. That is, if we know the total sum of squares and we know the within group sum of squares, then total minus within has to equal between because they're additive. But we could calculate this one on its own, and it turns out to be pretty simple as long as you have all the different averages for the different groups. It's the simplest one to calculate, the simplest sum of squares to calculate, because there's the least calculator entry. In this case, I'm taking the mean of group 1, 21.8, minus the grand mean, squared, times 10. The times 10 part is to weight this in case we have unequal numbers of people in each group. In this example, I have equal numbers, but this is actually a weighted variance. If I calculate all those deviations squared and add them up, in this case I get 233.867. So all my sums of squares are listed at the bottom. My total sum of squares from 2 slides ago is 769.467, and we know that we can decompose that variance into two pieces. The part that's due to the within group variation, the thing we just calculated for the between group sum of squares, and that's 233.867. And part of it is also the within group or error or residual part, which is the within group sum of squares, in this case 535.6. Our next step is to take all these numbers and put them into a table to allow us to calculate the mean squares and finally the F statistic. So here's the table I created by hand after calculating those three sums of squares. Always put your between, within, and total in that order, and understand that between plus within is equal to total. Degrees of freedom are very simple. The between group sum of squares is simply j minus 1. I have three groups here, slow, normal, and fast, and so I have 3 minus 1 degrees of freedom. My within group sum of squares is pretty easy to get as well. It's simply n minus j. I have 30 students, three groups, so 30 minus 3 is 27, and then our total sum of squares is equal to n minus 1, or 29. The next column is our MS, or mean square column. 233.867 divided by 2 is 116.933. That is, between group sum of squares divided by its degrees of freedom is the mean square between. 535.6 divided by 27 is equal to 19.837. That is, our within group sum of squares divided by its degrees of freedom is our mean square within. The ratio of those two mean squares, mean square between to mean square within, or the 116.933 divided by 19.837 is our F statistic, 5.895. With this table, putting all these numbers in there, working our way through to the F statistic, we're now in a position to compare the F that we observe, F calculated, to the F that we should observe, or the largest F we should observe if chance is operating, 3.35. Because we exceed 3.35, we're going to reject the null hypothesis with alpha 0.05, 2, and 27 degrees of freedom. Notice at the bottom of the table I've also given a p-value. Remember what a p-value is. The p-value is the area under the sampling distribution greater than the statistic you've calculated. So if we had an F distribution in front of us, we know that with 2 and 27 degrees of freedom, if we cut off an area in that F distribution starting at 5.895 and measure the area under the tail out to the larger F values, it would cover 0.0017 of the F distribution. And therefore, we could compare the P statistic directly to our alpha value. If our alpha value is greater than P, or P is less than alpha, then we're going to reject the null hypothesis. You should always get the consistent answer here. That is, if you reject the null hypothesis based on your F statistic, you should also reject it based on your p-value.